Hello and good morning. Welcome to my talk about NDT 4.0, which is also discussing flexibility and adaptability in NDT, especially as the whole industry is facing the new normal caused by COVID-19. But before I start, let me quickly introduce myself. My name is Lennart and I'm General Manager of VisiConsult X-Ray Systems and Solutions. We are a provider of high-end automated computer tomography and X-ray inspection systems worldwide. And to especially support your region in the Middle East, we have just opened another office in India to increase our local support and manufacturing capabilities. But let's get started. So, Industry 4.0 is the starting point of NDT 4.0. So this is where it all originates from, and this is where we also see many parallels. So Industry 4.0 or NDE 4.0 is a conglomerate of technologies. This includes augmented reality, robotics, simulations, Internet of Things, but we will go through many of these categories within this talk, and I will elaborate on them, giving you some practical implications for practitioners in the field. So before we look at this technology in special, let's step back and identify what kind of technology or what kind of innovation is Industry 4.0. And if we look here, we have incremental and sustaining developments. This is like minor improvements, incremental improvements towards a better process. Radical improvements are stuff that's just that's very innovative, but most likely not very sustainable yet. The impact is limited. This could be, for example, 3D printing, which is just starting to pick up. On the other hand, disruptive innovations, this is really stuff that is changing the way we work. It's changing. It's having a real impact on the industries out there. So, to give you some examples, why is NDE 4.0 disruptive? One big paradigm shift that we are talking about at the moment is that NDT is transformed from being end-of-line inspection, a pure quality gate, towards an industrial sensor. Because what we do in NDE, we get a lot of data and information about manufactured parts. This means every part that passes through the NDE gate gets inspected. We gain input about where are defects, how are these defects looking like, how these defects are changing over time. So we are a big data sensor for this bigger network of IoT sensors, which is giving process information. And this could lead to self-controlling manufacturing lines, to early warning signs. So this has huge implications for the way management and professionals see NDE. We are really moving away from a pure quality process towards an intelligence process. This is giving data about ongoing processes. And this data can, of course, be used by manufacturing engineers, operational engineers, to improve the manufacturing processes, to prove the methods being applied. This is a huge shift. But also the usage of digital twins. So more and more, we can use digital twins to simulate performance of parts in real life by applying loads, for example, by doing like finite element method analysis that try to evaluate the breaking points of parts, how they operate under stress. But we can also, through digital twins, observe trends. How does the part change as we change manufacturing processes? So we can create a kind of a digital twin of the actual part, which is enriched by all informations from the manufacturing process. And this is again where NDT as a digital sensor in this network can feed in data and can feed in information. It can be very valuable. But also augmented reality. The usage of augmented reality to assist operators, to help them to track, to find defects, to troubleshoot systems, to formalize techniques or inspection protocols into a digital workflow. but also the opportunity for level 3s, for example, to remotely assist their employees on the shop floor with advice, with second level scrutiny. So there's a big advantage of using augmented reality in our industry, and NDE 4.0 is just bringing this. So, but before we get started with the actual examples and with the real stuff, I want to give you one word of warning which you should consider throughout this whole talk. You might get excited when you hear about these new technologies. You might think, wow, this is great. We have to do this. This is nice technology. But you have to be careful that you don't just apply this NDE 4.0 concept to anything. There's a good quote here by Mr. Maslow. If the only tool you have is a hammer, you tend to see every problem as a nail. So if you now think NDT 4.0 is your hammer, then you shouldn't apply it to everything. What you should look at is at the total cost curve. So investments, for example, in NDT 4.0 should increase the costs of production. So it should increase the efficiency, it should decrease the amount of scrap, it should decrease the amount of false positives, for example. There should be an improvement. And after every investment, the total cost of your process should be lower than before. On the other hand, I know that many people are afraid and concerned with those developments happening. They're happening at a rapid pace. We are moving from an analog world to a digital world. So many people are going along like this. These guys, it could be, for example, people that still use film in certain environments. And somebody comes along with digital technology, digital detectors, with automated evaluation, cloud connection, and it would make the life of those guys much, much easier. But they say, no, we are so busy, we can't use it right now. These are the guys here. If you invest too little, your costs can actually be higher than if you invest and drive down your operation costs. So this has to be kept in mind. Don't innovate for the sake of technology. Innovate because it makes sense, because it drives down the costs of your operation. It makes you more efficient. Please keep this in mind throughout the whole talk. So let's start with an poll that I've done online on LinkedIn, and we had nearly 200 participants from all around the world from the NDT industry. And my question was, how will Corona or COVID-19 impact NDT? And most people were very sure that there will be an increase in automation efforts. And automation efforts, this can be also explained within the NDE 4.0 scope. So what kind of changes do we see? We hear a lot about the new normal. The new normal means the time after Corona, after the crisis. And many people are asking themselves, what will happen? What will happen to our industry? So we see, for example, many employers are sending their people into home office. And many professionals say this will probably remain in the future. We will probably work from home far more often than in the past. So can we also do this in NDT? Can we inspect from home? And of course, there are many challenges. Ambient conditions like lighting standards that don't allow this, customer certifications that are not yet granted by the OEMs, acceptance protocols are not yet developed. There is many question marks, but is it in theory possible to inspect from home? And the answer is not always, but some industries and some methods definitely allow something like this. So look at this example, for example, here. So we have two locations. This is a global company, right? It has two locations, one in country A, one in country B. So these two sites, they produce parts. They come on a palletized way into a system. In the one factory, they have less parts, so they have a quite manual system using manual labor to load it. And in the other factory, they have a robotic system. So you just drop the pallets, it's automatically inspecting the pallets. So what happens after inspection? The inspection data goes into a cloud storage. So it goes online and sits there. At the same time, the parts move into a consignment storage. They get put there and they get marked in a traceable way so that you have a serial number for each part. And then operators from a remote location log in to the cloud database and inspect the parts in their own tempo, in a distributed team, and the results go back to the central server location. And once a certain pallet or a certain batch is inspected, there's a dashboard showing the inspection results, showing that the pallet is good to go, and then the parts get processed. At the same time, we are archiving the inspection results online. And this is a breakthrough. Think about it. No more big film archives, no more manual film development, manual comparison between parts and film. It all goes online. People see a picture of the inspected parts. They see the position of the manipulator. They see the X-ray result and make decisions completely from away. Of course, there are cases when, for example, we talk about a mobile inspection, like on pipelines in the field. There's challenges to this. Also, some NDT methods that are not X-ray definitely have their challenges, like visual inspection or magnetic particle inspection. For example, will for a long time need manual local decision making. But we are seeing more and more that the reading and evaluation of a part is moved away from the acquisition of the X-ray of the inspection data, and this is changing the way we can work. Because, as I said, we can start to introduce cloud technologies, online storages. We can bundle data coming from different sites, and this is also allowing to have a specialist NDT team that's sitting in one location and is serving all other locations. And you can really also roll this out into a portable world. There is no reason why you couldn't have like a 4G or soon even 5G connection on your portable X-ray set. You acquire the images in the field at a pipeline or on an oil rig. You send them online to an evaluation center, and this is where people are sitting and doing online interpretation and assisting the inspection crew on site. It's a great advantage for the process. But of course, in factory settings, we need to rethink inspection. Right now, it's a single part flow most of the time, or a batch part flow. We think in shots, we think in films, we think in anachronic processes. In the future, we will see far more robotics on the shop floor. They will be used to move parts, to automate processes, to make it efficient. And also, if we talk about COVID and impacts, of course, having robots working in a proximity is much safer from an infection standpoint than having many humans working there. So we have to find a way to keep the production flow running without being disrupted by an epidemic or by any other type of disruption that might happen. So these kinds of automation tools, and we will see them later within this NDT 4.0 talk, will play a big role for sure. And when we talk about workflows, we don't have to go into the details here. If you're interested in it, I can give you some publications that deal with the new digital workflow of NDT processes. But for now, it's important that we kind of have a physical thread, and this is where the parts go through the factory, and we have a digital thread, which is the digital information that moves along with the part in kind of the digital twin. So we start with documentation, go into testing, we archive raw data, go into data processing, interpret, and archive and document results. And in the future, this whole red bracket will be replaced by proprietary automated systems, like for example, a rather automated CT system and a robotized digital radiography system or any other. So the whole process simplifies a lot because this system is generating its own data, it's documenting it, it's writing it into an archive, and you have digital techniques, which means techniques that are programmed into the system and don't have to be observed and controlled by an operator. So what we will have throughout this talk is an opportunity list. Because yes, all these disruptions and new technologies, they pose many challenges, sometimes even problems. But I want you to think about this as opportunities. So let's add to our opportunity list. Digitalization enables new work concepts. And this means workplace attractiveness increase, reduce costs because maybe no night shifts are needed anymore, reduce space requirements. And cloud applications allow connected systems. And this means lower training costs, higher quality, and of course, overall reduced costs of inspection. Which brings us to the next topic. We talk about artificial intelligence, or in X-ray we call it ADR, automatic defect recognition. So the goal is to have algorithms that help to detect defects or indications in parts. And we all are aware of the efforts of global car companies to develop self-driving cars. So if self-driving cars are on the horizon, there should be no reason why we shouldn't be able to have self-inspecting systems. And this means systems that automatically find defects based on certain acceptance criteria and make decisions based on it. And here's one example of an electron beam welding line. It's a very smooth welding line, nothing compared with like pipeline welds. So this is based on very thin aluminium plates that are used in the aerospace industry for fuel lines and hydraulic lines. So of course we have many more defect types, right? But I want to focus here for now on porosities, inclusions. So we have to the goal is to find those porosities, inclusions, or aggregation of porosities inside the part. And this is what an AI system does. It evaluates the it identifies defects in a binary way. So it finds all these red dots, and then it uses a logic. And this is also where the AI comes into the place, and decides, okay, this is because of certain criteria, is not just for porosities, but this is an accumulation of porosities. And the reason is that the distance between the porosities is too small. And it could be many more, like here, a single gas cavity, or in here, it's too many porosities on a certain area that was defined. And ultimately what we get out is a statistic. And this statistic is showing us an analysis, what kind of porosities are in a certain part, in a certain batch. And of course, by plotting these statistics over time, we can get an idea. For example, the welding engineers, they optimize the welding parameters. So what does happen now? Do we get less defects? Do we get less porosities? Do we maybe get more inclusions? So we can give a rapid feedback to the welding engineers on what process improvement happened based on their changes. And this is one sneak peek I want to give you. I can't tell more for now, but we are working on a new AI system for casting parts. And this is the image looks quite boring, but this is actually, if you're into data science, really cool, because what this image is giving you is not just a pure segmentation, but you get probabilities assigned to the segmentation. So we are not only working on pure thresholding like in the past, but we are really working on a neural network, on an artificial intelligence, which is interpreting features in the image, then assigning probabilities to every feature, if it's a defect or not, and then segmenting it and making a decision. And this is what will change our world. And obviously, it does not mean that immediately we will have AI implemented and no inspectors are needed anymore. That's not the case. It will probably first start as an assistant system. This means the AI will support the operator in making its calls, because the AI will probably need time to get trained to get the same accuracy and the same probability of detection, or POD, as the operator. So we require time and training data to grow the AI. But within the next years, we will see more and more automated systems, automated evaluation systems being deployed in practice, and the role of operators will change. We as NDT people will focus more on supervising the machines, training the machines, programming them, and making sure that their data is up to reality. So this is a big impact. So we add to our opportunity list. Artificial intelligence and ADR get better and will be deployed in practice. And this is reducing costs and giving a higher throughput. But so much to AI. Let's dig into simulations or digital twins. So I've already talked about the side of the digital twin on the parts. So you can create, using NDT, you can create a digital twin of your part. But also, your NDT system is more and more becoming a digital twin. And this means that you will have a digital world where your system is living in a digital space, and you have the actual system, and this is the physical representation of the digital system. So by using offline programming software, you are able to offline program these actual systems without even touching it. And the big advantage is that if you use your system for production, you don't want to shut it down for a week to create a new part program, to create a new inspection sequence or new technique, but you want to do this completely in the digital world. And then it's being transferred on the motion controllers and being tested in practice. The other example is, once you created the system, the program for one system, you have a second system in a different facility, you just copy the program and you're good to go. It's really making a difference. And this goes obviously beyond just basic programming. This goes even into feasibility studies and complete complex robot programming. So here, for example, is a case study we did with an oil and gas manufacturer. And the complexity here is that these tubes in here, they are leveling gauges for fuel tanks and oil and gas equipment. So these lengths can differ in a huge variety, because they can be very small, from like this big to 6 meters long. So, and also they have these flange configurations, and there are 20 different flanges that can be put in any space on this pipe, which is already changing dimensions. And this is a huge complexity. I mean, it would be impossible, and I mean literally impossible, to program this in a normal robotic system. So what we did is we came up with a system which is pulling the exact configuration from the manufacturing enterprise system, and then the robots are adapting to the actual parts. And this is actually great, because the only thing we program is different modules for different flanges and different flange configurations and pipe flange configurations. And then, based on these modules, the actual inspection process is created on the fly. So as the part gets loaded, you scan the QR code, and the system knows, okay, this is a 5 meter long part with 3 flanges in those locations and those flange types. And then the system takes all these robot modules, recombines them to one inspection sequence, and generates the trajectory of the robots automatically. This is massive, because in the past, if you had a high part variety, you were not able to automate using robotics because the variety was too high. Robotics were too inflexible because you need to spend a lot of time programming them. But by using flexible approach and digital pre-programming, you are able to now do this. And now comes the next big step. We are combining this trajectory or movement programming or simulation with X-ray simulation. So what you see here is, on the right is the real X-ray image, and on the left is the simulated X-ray image. What you can see is an image that looks nearly alike. It's very hard to tell the difference. So we are able, with just having the CAD data, just the drawing of the part, we are able to simulate how an X-ray image should look like. We can simulate what the image quality will be, we can simulate what the contrast will be, we can simulate what defects we can see if we can penetrate. And if you now combine the movement planning or the movement simulation and the X-ray simulation, you are able in a digital twin to really perform a digital inspection, make sure that you have all angles covered, and this will probably drive down the generation of techniques and the programming of systems drive down to a minimum. And it will make your life easier, ultimately. So, digital twins with actual data provide added value beyond NDT and provide a better traceability. This is a huge advantage. Also, offline simulations of inspections. This means less downtime, higher efficiency, earlier proof of concept. Many advantages. And this is really bringing us to the end of the first part, which is which is showing where we see NDT 4.0, especially in the X-ray world, really making a big impact on our everyday work and on the future of our industry. And this is the automation, using robotics, using advanced CNC systems. Well, the robotics are here as well. This is mainly the simulation, the offline programming. Robotics as well, using autonomous robots, using industrial robots. Cloud connectivity, linking up systems, linking interpreters, operators up with systems, getting customers on board. This will be a huge, huge difference. Simulation of X-ray images, getting a proof of concept before you actually have to have the system on the part on your system. Also, if you're an inspection company, you might want to know, can I really inspect this part I'm quoting on my systems that I have? So you can just ask your customer, please send me your file. I do a pre-simulation. Oh yes, I can do it. And it's taking me 2 hours to inspect it. This will make your quoting accuracy much better. Artificial intelligence will come. We are seeing it already being deployed in practice now, mainly as assistance systems. In automotive, they are already standalone. So brace yourself, there will be a change. And last but not least, there will be computer tomography, a big push on the three-dimensional world. But I will address computer tomography in the last section of this talk on the use case of additive manufacturing. So let's close our opportunity list for the first part of NDT 4.0 and let's wrap up. There's many chances and opportunities. Be careful. There's also pitfalls. There's also complexities. Technologies are not adopted easily. Please think about the hammer and the screw. Not everything that you see out there is a nail. NDT 4.0 is not for everybody. It really depends on the application. So please be careful with where you apply it. But if you identified the right use cases, you can have immense savings. So the last section will mainly focus on additive manufacturing and computer tomography, because that's a very special and highly quickly growing field of NDT 4.0. So you all know additive manufacturing, that's this crazy additive technology versus subtractive technology that's able to transform clumsy CNC milled structures into bionic, fancy things that can solve many problems, because they can reduce the weight, they can have a higher durability. But why is that a problem for the NDT sector? Because there are companies that are starting to bring these additively manufactured components in safety critical environments like turbines. And the image here on the left, this is no additive manufacturing failure, so bear with me, as there are so little flying parts, so I don't have a picture showing an actual additive manufacturing failure. But even with traditional NDT methods, you see failures on parts. Like here, it was a fan disk failure because a crack did not get noticed. So it led to an uncontained engine failure. Pretty critical. But as we are now bringing additive manufacturing into these turbines and critical environments, we have to be absolutely sure that what we do can be inspected and can be inspected well. So let's look at the additive manufacturing process chain. Where are we? So data processing is the first step that happens. So somebody creates the part. It's typically design engineers. Then the additive manufacturing engineers are transforming these raw data into layered data, because this is what the additive manufacturing machine needs to build layer after layer in an additive way. And once it's built, you will have some kind of post-processing. You need to remove the support structures. You need to do maybe some surface treatment, maybe some heat treatment. You need to get rid of residual powder. There's many steps that are required here. So once this is done, it's our part. We come to quality assurance. Of course, the visual inspection needs to be right. And then there's a lot of computer tomography required to really find all the potential defects. And also coordinate measurement is something that NDT can really assist with. And then, of course, and for some cases, you need to do some destructive testing, some tensile probes and stuff like that. And this is finally leading, hopefully, to a successful acceptance test. So why am I stressing this so much? Because in additive manufacturing, defects are different. In casting and welding, these are all technologies that have been known for years, maybe for hundreds of years. So we kind of know how they act. We kind of know how pores look like. They are typically round in castings. We look like cracks, how they start. They come from crack kernels, maybe some residual stress on the part. We know these defects, but the challenge is in additive manufacturing they look different because due to the layered approach, porosities are not round anymore necessarily. They can be, they can have edges. They can look like this. They can have a starting point for a kernel for a crack. Also, cracks originate from different areas. We have a lot of residual stress, a lot of temperature gradients in additive manufactured parts. This can really cause a different cracking image that we've seen in the past. But also delaminations. This is something we've never seen before in most of our manufacturing technologies. But now with additive manufacturing, it can be that laser energy is not quite enough to really fuse the powder of the layer. And if that happens, you have a layer of very thin particles, maybe 30 to 50 micron, that is not molten, so that is not fused completely. And this is called the delamination. So it can be a huge issue if your whole part looks good from the outside and in the middle there's a complete layer that's not fused at all. This can lead to a severe part failure, and you will have to find a way to inspect it. And of course, inclusions also can happen, particles of higher densities brought in by the powder. So the issue that we have right now is that there is no good volume of standards available that's telling you what is the acceptance reject criteria of additive manufacturing parts, what do I need to look out for, what is already critical. And that additive manufacturing can build crazy structures, and typically everybody is trying to reduce weight on additive parts. We also go into much lower thresholds. So we go into dimensions and areas where typically you wouldn't go on a casting system, just because you cannot build such structures with a casting process. And to make it even more complicated, most NDT methods are not working very well on additively manufactured parts. Ultrasonics, for example, very hard on these complex structures. You have lattices, you have bionic features. It's very hard to do a proper UT scan on additive parts, if not impossible on most of them. Penetrant, critical, because you have a high surface roughness, so that means the whole part will be glowing. Penetrant is possible if you did a proper proper surface treatment, but also for the whole internal passages, internal structures, lattices, you can't use penetrant. So most specialists are of the opinion that probably CT is the best and most accurate inspection for additively manufactured parts. And this is how it looks like. You have the real part here. In this case, this is a casting part, but it shouldn't matter. It's just to show you the different results that you get. So here on the casting part, of course, you can do a real cut. So you can cut the part, you can look at the metallographic structure, and you can look for porosities, inclusions, cracks, and stuff like that. But with CT, you can create a three-dimensional model of the part. You can create the perfect digital twin of your part. And then you can virtually create cross-sections and perform analysis like porosity analysis, for example. And this is now a real additively manufactured part. It's a tensile probe. It's a dog bone that was used for destructive tests. And what we did here, we tried to correlate where do we find defects in the parts, and will this be where the part will be failing under tension. And what we found here is certain inclusions, the white spots. We find porosities in here. This whole scan has a resolution of 5 microns, so it's a quite high resolution. So we're talking about small defects. But this is what you have to find at some point, because as you can see in here, the part is not perfect. It's not homogeneous. You see a lot of porosities, you see a lot of inclusions, which will have an impact on the integrity of the part. And yeah, this is the three-dimensional rendering where you can see how the defect distribution changes through the part. And this is really the data that additive engineers need to know. They need to know how they have to change their process and how to optimize it to get better parts. And this is again another time we see the paradigm shift of NDT. We are not only telling manufacturing accept or reject, but what we are actually telling is where they need to improve. We actually add value beyond the pure quality control, and this is big. Another big thing in additive manufacturing is residual powder. So what you see on the left is residual powder left in additively manufactured parts. It's a heat exchanger here that is a great design. It's amazing what you can do with additive manufacturing. It's impossible to manufacture such a part with traditional techniques, but you see on the inside, in the CT scan on the left, there is some residual powder. Here, the whole internal passages are clogged. Here you see powder. And if you cut the part, you see at the same areas. You see it's all filled with powder. And this can be critical because a heat exchanger only works if heat is actually going through the part. So having these internal residual powder can be an issue. So it's good that you are able to detect it and find it. And I've talked about measurements. You can perform, of course, traditional measurements using a CMM, but you can also use a CT system, doing wall thickness measurements, doing complete part measurements and dimensioning, measuring angles, measuring wall thicknesses. And the great thing is that you can do this also on internal passages. So on this part, for example, you're not able to measure internal passages within CMM. You are only able to measure the outside and assume that the inside is okay. But by using CT, no problem. You can measure also internal structures. And ultimately, I've already told you in the beginning, the digital twin of the part is becoming more and more important. Running simulations on complex parts that are put under a lot of stress is important. So what you see here is a bracket that's used in an aircraft. And what you see here is that you have load bearing points inside on this object, and then you apply cyclic load in one direction. And you can see the load distribution through the part, and you can see how it behaves and when it will break. And obviously, you can also do this with the CAD data, but what you have included into this simulation is all defect data, all the porosities, all the geometry deviations that will help you to make an educated call. And talking about educated calls, a big problem of additive manufacturing is that you might have geometric deviations. This can be because the whole object shifts inside the envelope, built envelope, or this can be because of residual stress in the part caused by the temperature gradient. So the whole part might bend in one direction. And this is what you see here. You see here a lot of inward bending, and on the outside you see a little bit of outward bending. And this can be critical for the tolerances of the part. So when you analyze this in a cut, then you can see that, especially on the outside, you have inward bending structures, and in the center you're okay. So with this data, a manufacturing or additive manufacturing engineer can come and say, okay, this is here I need to optimize, here I need to optimize, and then bring the results into the desired effect by changing the additive manufacturing parameters. And this is actually what can be done quite easily. Changing or analyzing how the part is changing, how it's if it's bent or if it's displayed, or how it's deformed ultimately. And if you are interested in learning more about additive manufacturing, we put out a free white paper. Just scan this barcode or send me an email, and I will happy to follow up on this and send you a free white paper showing how surface treatment and CT scanning are able to improve the quality of additive manufactured parts. So yeah, please feel free to follow this link. Ultimately, I want to say thank you for your attention. It was a pleasure to be invited here and speak to you, to this audience. I hope I was able to give you some more insights about the state of the industry in terms of NDT 4.0 and additive manufacturing. Of course, this is just a teaser. On every single topic, I could probably talk an hour. But this is just giving you the overview. If anybody of you wants to have more information or learn more about the technologies, please feel free to send me an email, to contact me on LinkedIn. And I want to point you towards one last thing. We have a free mobile application. It's called our NDT X-Ray Toolbox. You can find it in the App Store and the Google Play Store. And again, it's totally free, but it helps you to do geometric calculations like unsharpness, optimal magnification. It helps you to calculate CT projections and energy. And it also has a compendium of all X-ray standards, ASTM, ISO, ASME. And it's allowing you to transfer IQIs from, let's say, hole type to wire type. So feel free to download it. And also, if you have some feedback on this application, I would be happy to receive your message. And I wish you a great conference and a great day. It was a pleasure to be here. Thanks a lot.